So we'll continue the problems on stiffness method, and we have taken one problem in previous class. So let us go to the next problem here. Okay, so this is our next beam, which has to be solved by the stiffness method. Okay, so in this case, so what you have to do is analyze this beam by stiffness method and draw the SFD and BMD. Okay, so the loading are here, what are shown. So it is a two-span continuous beam with the overhang portion over here, CD of 1 meter. And we have these two concentrated loads on span AB, and on span BC, there's a UDL over there for a length of 4 meters. So here, if I now first determine the degree of kinematic indeterminacy, I'll come to know that it is 2. Clearly, by seeing here, I can say a rotation at B, at joint B, rotation is allowed, and even at joint C, rotation is allowed. So these are the two unknown displacements, what are there existing in the beam. Okay, independent displacements. If I know theta B, theta C, rest other displacements can be calculated. So these are independent displacements, theta B and theta C. So that tells me that the degree of kinematic indeterminacy dk is 2. Okay, so dk is coming out to be 2, and the unknown displacements are rotation at B and rotation at C over here. Okay, now after this we'll go for assigning the coordinates. So since this is having a degree of freedom or degree of kinematic indeterminacy as 2, we'll come across 2 coordinates corresponding to the two unknown displacements. So here the location of coordinates is fixed. The two coordinates, they will come at joint B and joint C, because the displacement what are existing, they are at B and C, theta B, theta C. So the location of coordinates will be at B and at C. We are free to choose the direction and the number, the coordinates. The order in which we want to number, we can go ahead with that. Okay. So what we'll do is we'll take clockwise coordinates. The direction of coordinates will take it to be clockwise for both the coordinates, and at B we'll take the coordinate number 1, and at C we'll give the coordinate number as 2. Okay, so these are our two coordinates. Now the direction what we have is in clockwise, and the coordinates numbers are 1 and 2. Okay, in this order I have numbered them. Okay, there is no restriction that the coordinates have to be numbered in this order only, or the direction should be clockwise only. Okay, the user is free to choose the order in which it is done, the coordinate orders, as well as the numbering of the coordinates. We can choose it over there. Okay, so it is better if we follow one direction for all the coordinates. That is, if I'm taking first coordinate in clockwise direction, second also I'll keep it in clockwise direction. It is just for convenience in solving the problems for our purpose. Okay, so that is what I have done is the coordinate direction I have taken clockwise. Okay, for both. At B, the number is given 1, coordinate is chosen as first coordinate, and at C, it is taken as second coordinate. Okay, now with this, I can now write what is the displacement matrix here. Okay, so displacement matrix delta will consist of all the unknown displacements that are there in the structure. Okay, for us the unknown displacements are 2, theta B and theta C over here. So this will be put in this displacement matrix. Okay, so delta displacement matrix will consist of theta B and theta C. In the first coordinate, the unknown displacement is theta B, rotation at B. In the second coordinate, the unknown displacement is theta C, rotation at C. So in that order, they have been taken in this matrix. Okay, this is our one of the matrix, displacement matrix. Now, once I finish with this displacement matrix, I'll go ahead with determining the force matrix over here. Okay, so the first force matrix, what I'll be determining will be the forces in the coordinates due to the loads which are present on the members. Okay, so you can see there are concentrated loads and there is a UDL which is applied over the members, member AB, and on member BC there are loads which have been applied. So due to these loads which are applied on the member, what forces will develop in these two coordinates? I want to know that. I want to determine those forces here. Okay, so for that purpose, okay, I'll just simplify this beam first. Okay, this is a beam with overhang portion. Okay, now how we are going to work with this overhang portion? Okay, what I can do is in this beam, I can replace that overhang portion by a equivalent force and a couple system here. Okay, I'll bring this 60 kilonewton force over C. Along with that, what will come is the moment which it was producing when it was at D. Okay, so when it is at D, it is having a moment of 60 into 1 meter. 60 kilonewton meter moment is produced at C. Okay, due to this 60 kilonewton load. Okay, so now I'll bring it at joint C itself. Okay, so this entire beam can also be represented in this form. Okay, I removed the overhang portion over here. Instead of that, what is done is equivalent force and couple has been placed at C over here. Okay, 60 is due to 60 into 1 meter, 60 kilonewton meter. It is having clockwise direction. Okay, and this force will shift as it is in downward direction over C. Okay, this is the simplified form of this beam what we have here. Okay, I just removed that overhang portion, and whatever the forces or the moment it was producing at joint C have been applied over here in this one. Okay, now let us go ahead with determining the P dash matrix. Remember, P dash is the forces in the coordinates due to loads applied over the member. Okay, due to the loads which are present over the member. For that, what you have to do is you have to restrain all the displacement in the coordinates. Okay, we have coordinates at B and C. So you need to make these joints B and C fixed. Okay, you restrain all the displacement in these two joints B and C. That is, don't allow any rotation to take place at coordinate 1 and at coordinate 2. Okay, for that a fixed support will be introduced here at B as well as at C. Okay, now once I do is that what I'll get is two fixed beams like this. Okay, so AB. Okay, I can take this separately as AB, a fixed beam. Similarly, BC as a fixed beam, I can treat it like that. Okay, now you determine what are the fixed strain moments that will develop at these joints. Okay, so define the fixed strain moments in these two beams. MFAB, okay, WAB square by L square. Okay, for this 20 kilonewton load, WAB square by L square comes out to be 8.88 minus 8.88. Okay, and when I take this load, it will be again 20 into minus 20 into 2 into 1 square by 3 square, which comes out to be 4.44. Okay, so you can do that calculation, and what I get here, okay, if I apply that equation, so I'll be getting it as total fixed end moment at A MFAB will be equal to minus 13.33. Okay, so this is nothing but this will be equal to MFAB, sorry, this is MFAB. See, just one calculation, let me show it. Minus what I have is WAB square by L square, is given by this equation. So in this case, there are two loads of 20 kilonewton. So for the first load, for this load, if I take A and B, it is 1 meter and 2 meter. A is 1 meter, B is 2 meter. Okay, so minus 20 into 1 into 2 square divided by 3 square. Okay, minus for this, if I consider the next load now, for next 20 kilonewton load, minus 20, what is A here now? Now A is 2 meter up to this load distance, into A is 2 and B is 1 meter here, into 1 square divided by 3 square. Altogether, this is coming out to be minus 13.33 kilonewton meter when you calculate and add this. Okay. On the other side, since the loading is symmetric, the fixed end moment will be same but with opposite sign, plus 13.33 here. Okay. So that is the calculation for fixed end moment in span AB. In span BC, what you have? the MFBC value, okay, WL square by 12. So MFBC will be minus WL square by 12, whereas MFCB will be plus WL square by 12. Okay, so what values I am getting here is minus 53.33 and plus 53.33 are the fixed end moments for span BC here. Okay, now when I have these fixed end moments calculated here, now what I am interested in is what is the total force in the coordinate 2. I want to calculate what is the total force in the coordinate 2 due to the loads applied over the member. For that, I'll be adding MFBA plus MFBC. Okay, MFBA, MFBC, both are at coordinate 2 only. These two fixed end moments are acting at joint B. Okay, joint B is common to these two spans. So at B, I have my coordinate number 1. Okay, so what will be the net force in the coordinate 1? The total force in the coordinate 1 due to the applied loads, it will be MFBA plus MFBC. What will be the total force in coordinate number 2? It will be simply MFCB. Okay, MFCB. Don't consider this loads which are coming due to that overhang portion here only. Okay, they are not taken in this. Here, what I'm considering is only the loads which are applied over the member, directly on the member. Okay, not directly in the coordinate. Over the member, whatever the loads are applied, due to that, what forces are being developed in the coordinate 1 and in coordinate 2 that I'm calculating. Okay, so what I get P1 dash. If I want to know P1 dash, I'll be adding MFBA and MFBC. Okay, MFBA and MFBC, right? So that will give me P1 dash. Similarly, P2 dash will be nothing but MFCB itself directly. Okay, P2 dash will be here, MFCB. So P1 dash comes out to be 13.33 minus 53.33. These were the two fixed end moments over there. So it comes out to be minus 40. MFCB is coming out to be P2 dash MA is equal to MFCB, which is 53.33. Okay, so 13.33 minus 53.33, this will come out as P1 dash, which is 40 kilonewton meter minus 40 kilonewton meter, and P2 dash is nothing but MFCB, which is 53.33 kilonewton meter. So I have my one of the force matrices. Okay, P dash. So P dash is consisting of this minus 40 and 53.33 kilonewton meter. In the first coordinate, whatever is the force here due to the member loads, it is written here. In the second coordinate, whatever is the force due to the loads applied on the member is written here. Okay, how we got this is by taking the fixed end moments. Okay, now the next step, what we are going to do is develop the stiffness matrix. Okay, so how do I develop the stiffness matrix? I have to take each of the coordinates. Okay, each of the coordinate at a time, give unit displacement in the coordinate, and find what forces are developed in every coordinate or all the coordinates. Okay, this is the way in which we develop the stiffness matrix, right? So first is I'll take the coordinate number 1. Okay, so I'll give unit rotation in the direction of coordinate 1. Okay, and I'll see that there is no displacement or no rotation is taking place in second coordinate. Okay, the displacement should be given in only coordinate 1 here first. Okay, so give unit rotation in the direction of coordinate 1 only, right? So this member, okay, what is there at the coordinate 1? There are two members which are connected, BA and BC. So I have to rotate both of the member by 1 unit if I want to give unit rotation in coordinate 1. Okay, whatever the members are connected at that joint where your coordinate is existing, all those members have to be given unit rotation. Okay, so for that purpose, both of these members BA and BC have to be rotated by 1 radians or 1 unit. Okay, let us say 1 unit. So after doing this, find what is the force in the first coordinate and what is the force in the second coordinate. Okay, so K11, if I find what is force in first coordinate, it will be nothing but stiffness coefficient K11. Okay, force in first coordinate due to unit rotation or unit displacement given in first coordinate. So this is equal to 4EI by L. Now what is 4EI by L? 4EI by L for AB and for BC we have to consider. So 4EI by 3 for AB, okay, 4E into I by 3 for AB plus 4E for BC, it is 2I. 4e into 2i by 4. Span is 4 meter. Okay, 4ei by L for AB plus 4ei by L for BC. Substitute the respective properties of the spans. Okay, now if I add up these two, I'll get to know what is K11. Okay, K11 comes out to be 10 EI by 3. Okay, this is my K11 value. Right. Now at the same time, when unit displacement or rotation is given in first coordinate, find out what is the force in the second coordinate over here. Okay, so this is given by K12, force in second coordinate due to unit rotation in first coordinate, which will be equal to 2ei by L, half of this, whatever is there at the first coordinate, 2ei by L, half of this. Okay, so substituting the properties of I and L for BC. Okay, joint C. Okay, here is our second coordinate. So this span BC will come in consideration. So 2e into 2i by 4. I have substituted properties of I and L in this equation for BC. So that is giving me K12 as EI, simply EI here. Okay, so I got to know two elements of my stiffness matrix. Okay, K11 and K12. When unit rotation is applied in the first coordinate, right? Then we'll go to second coordinate now. So when I come to second coordinate, now let us go for giving unit rotation in the second coordinate and in the direction of the coordinate. Okay, it should be given in the direction of the coordinate here. Okay, so at joint C, where my second coordinate is there, I'll apply unit rotation over there. I'll rotate this member by 1 unit. Okay, and find what is the force in second coordinate and force in the first coordinate here. Okay, so force required in second coordinate for giving unit rotation, if you determine that, that will be K22, the stiffness coefficient K22. What this K22 means? Force in second coordinate because of unit rotation given in second coordinate. So this will be equal to 4ei by L. Okay, what are the properties here? It is for BC member. You are rotating BC member about joint C by 1 unit. So 4e into 2i divided by 4. Okay, these are the properties for member BC. 4e into 2i by 4. So K22, what it comes out is 2ei. Okay, similarly, if I go for finding what is the force in the first coordinate, when unit rotation is given in second coordinate, it will be K21. Force in the first coordinate due to unit rotation in second coordinate. So it is given by 2ei by L, or 2e into 2i divided by L, which is 4 meter. Okay, so K21 is coming out to be EI, just EI. Okay, and note K12 and K21, they are same. Okay, so that is what we have here. So I have 4 stiffness coefficients, which are nothing but the elements of our stiffness matrix. Stiffness matrix is of size 2 by 2 because degree of kinematic indeterminacy is 2. So the stiffness matrix will be of size 2 by 2. Square matrix, symmetric matrix. Okay, so all these 4 we have elements. Now I'll arrange them in this stiffness matrix. Okay, so what will be my stiffness matrix here? If I take EI outside, what we have is K11, K12, K21, and K22. That is how you arrange them. Okay, so K11 is 10 over EI, and K12 is simply EI. EI is kept outside, constant. So this will be 1. K21 was also equal to EI. So here 1 will come. K22 was 2 EI. So 2. Okay. So this will be my stiffness matrix here. Okay. The same, these elements, what 10 by 3, 1, 1, and 2 have been put in this stiffness matrix. They have been arranged over here. Okay. So you can see this is symmetric about the principal diagonal. That is a property of our stiffness matrix. And what we have size here is 2 by 2. 2 row, 2 column, 2 row, 2 column. This comes from what? The degree of kinematic indeterminacy of the structure. It will tell you what will be the size of our stiffness matrix. Okay. So after having this stiffness matrix, now what I'll be doing is we'll consider the condition of equilibrium for that beam. Okay. So each joint in that beam have to satisfy this condition of equilibrium. Okay. So total force or the net force in any coordinate is equal to force due to the displacement in that coordinate plus force due to the loads applied on the member in that coordinate. Okay. So here P is the net force in the coordinate. Okay. P delta is the force due to the displacement which are taking place in the coordinate P delta, and P dash is the force due to the loads applied on members. Okay, what force is developed in the coordinate due to applied loads on the members is P dash. Due to the displacements which are taking place in the coordinate, due to that what forces are developed is P delta. If you add up these two, it will give you net force in the coordinate. Okay, this P delta can be expressed as K into delta, because K was for unit displacements in the coordinate. K is the matrix giving me the forces due to unit displacement in the coordinate. If I multiply this by the displacement matrix delta, it will tell me P delta here. Okay, that is how we express the P delta. Okay, now further, what I have net force in the coordinate. Now, if you just look into that beam, okay, so the beam, what I have, I'll go back here. So you just look into this particular diagram here. Okay, so this is a diagram and compare it with the coordinate diagram, what we have here. Coordinate 1, coordinate 2. So coordinate 1, is there any force directly applied in the coordinate here? There is no such force which is coming directly in the coordinate. I'm talking the force which is directly applied in the coordinate here. Okay, so no, in the first coordinate there is no force which is directly applied in the coordinate. So P1 is 0. Okay, P1 is 0. Next, second coordinate is here at C. Is there any force, okay, in second coordinate directly applied in the second coordinate? Yes, it is there. Which one? This moment, because this coordinate 2 was representing a rotational coordinate. The corresponding force, a force which can cause rotation, is movement. So what will come in this P2 is the 60 kilonewton meter. See, this movement is also clockwise. Our coordinate direction is also clockwise. So what I'll be taking P2 is plus 60 kilonewton meter. So this is how direct forces come in picture in the coordinates. In the second coordinate, there is a direct couple which is being acting over here, 60 kilonewton meter. Okay, so that will come in that this matrix, P matrix. P1 is 0. There is no force which is acting in the first coordinate here. Okay, and P2, what you have in the second coordinate, I have this 60 kilonewton meter force, or the moment of 60 kilonewton meter. Okay, direction, it is in the direction of coordinate. Coordinate is also clockwise direction. This moment, what is being applied in this second coordinate, is also in clockwise direction. So P2 value will come out to be 60 now. Okay, so that is what I have taken here. P1 is 0. There was no force in the first coordinate. P2 is 60 kilonewton meter because there was a moment which was acting in the second coordinate in clockwise direction with a magnitude of 60 kilonewton meter. So this is put in this P matrix. First coordinate, no force. Second coordinate, 60 kilonewton meter moment in clockwise direction. 0 plus 60. This will come in this P matrix. Okay, now if I substitute all these matrices here, this is what we have. So this is P matrix, 0 and 60. So that will be equal to P delta, which is nothing but K into delta, stiffness matrix multiplied by the displacement matrix. So this was our K matrix here. EI into 10 by 3, 1, 1, 2. Displacement matrix, it was consisting of unknown displacement, theta B, theta C. Delta was equal to theta B, theta C, column matrix. Plus what? P dash matrix. We calculated the P dash matrix by taking the fixed term moments. So it was minus 40 in first coordinate, minus 40 kilonewton meter. In second coordinate, it was MFCB, which was 53.33. Okay, we have written this earlier, this matrix, P dash matrix, right? Now let us rearrange this. I want to calculate what are theta B and theta C. These are the unknowns. I'll take it on one side. So what happens if I take it on this side? 0, 60, minus 40 and 53.33. Okay, so if I rearrange the entire equation, what it gives me is theta B, theta C will be equal to 1 over EI, inverse of this matrix, 10 by 3, 1, 1, 2, inverse of this, into this P minus P dash. Okay, this is nothing but P minus P dash. Okay, so just if you rearrange this entire matrix, it will give you like that. Okay, so this entire P was equal to this K into the unknown displacements delta plus P dash. Okay, so what I want to determine what is my delta matrix. So it will be equal to simply this K inverse into P minus P dash matrix. So this is what I have done over here by taking or rearranging the terms. So finally, on solving for this matrices multiplication and all, if you do that, you will get theta b as 12.95 over ei. Okay, it is put in the matrix, but if you take up the terms, what it says is theta b is equal to 12.94 by ei, and theta c is minus 3.13 over ei. These are the values of displacements or rotations, theta b and theta c. Okay, theta b is in the direction of coordinate, that is, it is clockwise, whereas theta c is in the direction opposite to the coordinate direction, that is, the rotation at c will be in anti-clockwise direction. Okay, now these unknown these displacements should be substituted in slope reflection equation, or to get final moments you need to use the slope reflection equations, so which are given by MAB, which is equal to MFAB plus 2ei by L into 2 times theta A plus theta B minus 3 delta upon L. Delta is 0. There is no settlement which is taken here. So if you use these equations, maybe for AB, BC, BA, CB, okay, you'll be getting the moments, final moments. Okay. So that is how you deal with that problems. Here, what came in picture was a force which was directly acting in the coordinate. How these forces will come over here. Okay, so we got to know this one, how to deal with this overhang portion, or when you may come across this values in the P matrix. Okay, it was an overhang here, but maybe in some cases directly a couple may be given to you. If at all, if it is applied in the coordinate, then that will come in this P matrix. Okay, if not, if at all, if they are applied anywhere other than the coordinate, they will come in this P dash matrix. Okay, P dash is the force matrix which we obtain by taking the forces which are applied on the member. Okay, P dash represents a matrix. Okay, matrix due to the loads applied on the member. Okay, it represents the forces in the coordinate due to loads applied on the member. Whereas P represents the matrix due to the forces which are directly applied in the coordinate. Okay, P directly applied in the coordinate. P dash forces due to the loads applied on the members. What forces will develop in the coordinate that we are calculating here. Okay, so when you are taking P, remember if it is a rotational coordinate, then you need to look for moment. Okay, here P2 rotation, I've taken 60 kilonewton. This is kilonewton meter. I've not taken a 60 kilonewton load over here. The moment which was acting at C, 60 kilonewton meter, that is taken here. Okay. So if it is a rotational coordinate, corresponding moment has to be taken over there in this P matrix. Okay. So that is the analysis what we have. Let me know if you have any doubts in that part. Okay, this is the Bediman diagram, what we can have. So this will be parabolic in nature. Okay, shape. Okay, you can draw that diagram, but other than that, if at all, if you have any other doubts, tell me. Okay, so that is the diagram. So this is Hawking measurement negative Here also hogging unit negative. This is positive, sagging unit negative, hogging unit. This is also negative, hogging unit positive, sagging unit. This will be WL square by 8. So the value will be 20 into 4 square by 8. That will be 40 kilonewton meter. So 40 kilonewton meter here. This comes out about WAB by L 13.33. This is also 13.33 kilonewton meter. So here what was the value I got for this? So I'm getting 4.73 here, and at this point B it is 30.5. Here it is 60. So at points A, B, C, and D. In diagram you can write, but other than that, if at all it is anything difficult in the problem, you can tell about that. You can clear your doubts. Now, you can unmute yourself. You can ask any doubt if you have. So this will be about the beams. Next class, we'll go to frames and the trusses. So we have finished one part of the analysis, beams. Now question will come that if at all if settlement is there, okay, if at all settlement is given, then what will happen? In case of settlement, the moment due to settlement will be taken in fixed end moments. Okay, here when I am dealing with calculation of P dash matrix, in that matrix, in addition to this, say suppose if support B is settling down, okay, what I get is I'll have to calculate the moment due to settlement here, okay, minus that moment due to settlement should be added to this fixed end moments. It will be taken in P dash matrix, okay, in case if at all any of the support settlement is given to you minus 6ci delta by L square. Okay, so that will give you the moment due to settlement. That will be added over here. That is also a force which is developed in the coordinate due to the member loads. Okay, it will be taken into member loads. So P dash matrix will take care of that settlement if at all if it is given. Or else maybe like this. Okay, P matrix may have value whenever there is a load which is directly acting in the coordinate. Okay, so in this case, in second coordinate, there was a movement of 60 kilonewton meter. Okay, so this is my P2. This is where the P2 will come from. Okay, not this force of concentrated load. It will be movement P2. P1, what you have? P1 is 0. P matrix when you are writing the P matrix. Okay. Okay, we shall finish this, then you can give the attendance in the chat box. You can give your attendance now.